Sorry. Hi, everyone. My name is Khalid. I'm one of your BIOSA senior year representatives. Right before you start class, I just wanted to tell you about a cool event that we've got coming up. So BIOSA is hosting our annual graduate school panel, and I think this is something you'll want to check out if you're considering grad school, even slightly, like K-Masters or a PhD. So we've got a bunch of graduate students from competitive UFT programs coming in to share their experiences. They'll be talking about the application process, giving you tips and letting you know what helped them stand out. We're also bringing panelists from master programs like medical physiology, rehab sciences, medical genomics, translational research, applied immunology, and more. So, regardless of what your path looks like, there will be something useful for you. And even if grad school is not on your mind right now, if you're thinking about getting into research, this is still a great chance for you to connect. A lot of our panelists are doing research and are also supervising undergraduate students right now. So, you might meet someone who ends up supervising your future research. And yes, there will also be food. So honestly, come for the snacks and stay for the knowledge and the connections. This is all happening tomorrow, October 22nd, from 5 to 8 p.m. in HW216, and you can sign up through the BIOSA Instagram page. That's THEBIOSA, BIOSA, and you'll find it in the bio. So thank you very much, and I hope to see you there.
All right, so good afternoon, everyone. A couple of housekeeping things before we continue on with our lecture here this afternoon. The first of which is, of course, to remind you that we're currently in the midst of Term Quiz 3. So sometime by the end of the day today, you'll want to complete that quiz. And then the grades will get released sometime early tomorrow morning. And then that puts us into our rebuttal period. I'll turn that off. Puts us into our rebuttal period at that point. Yeah, you have until the end of the week to submit any rebuttals that you want to submit. And then, short communications are continuing. So don't hesitate to reach out if you have any concerns in that regard. I know that there are lots of people who are busily trying to meet that first bonus deadline, which I can't remember when it comes up. We may very well extend it a little bit, just because I know people have been like, hey, I'm working my ass off to try and hit this deadline, and the rate limiting step is sometimes the TAs, and they're doing their best. So we might extend that deadline. I just need time to sit and think about it and give you a new date. Yeah, but I like the bonus because it does encourage people to kind of get moving on the project. And that hopefully means that when the end of November rolls around, it's not like we've had in the past where there's tremendous numbers of submissions that need to be evaluated all at once. Anyways, that's all I had to say. Any questions about things before we get going? Everybody's good? Oh, look at this. A question. Yeah, what's up? Yeah? This is the same question I got this morning for my second years. I'll give you the same answer I gave them, which is I feel like the lesson we're supposed to take from this current Blue Jays team is this persistence and resilience and teamwork and collaboration, and that's what's the path to success, right? Yeah. Also, do you need bonus marks, really? You guys have been the first two quizzes were 85 and 80% averages. I don't feel like you need. It's like saying to the Dodgers, let's give you an extra at bat. I think you're okay. Good try though. I like the effort. Anything else? Okay. So we were talking on last Friday. We started talking a little bit about the speed of action potential propagation, and so we basically said that in order to get fast action potential propagation speeds, when sodium ions come in through open voltage-gated sodium channels, they need to spend their time traveling down the axon towards the axon terminals, within the cytoplasm of the axon. And the more time they spend doing that, the faster we're going to propagate action potentials. If, however, those ions start to leak back across the membrane, which of course starts to dissipate the membrane potential back towards rest. When that happens, then we have to start opening up other voltage-gated sodium channels downstream here to let in new influxes of sodium, and now we've got a lot of movement going this way, right, back and forth across the membrane. That's not helping us get our action potential down to the axon terminal. So that's what we need to do in order to get fast action potential propagation. We need to encourage sodium ions that come in through open voltage-gated channels. We need to encourage them to keep traveling down the cytoplasm of the axon. So in that regard, I introduced you then to this length constant equation. Effectively, the length constant here can be thought of as basically how far can sodium ions travel down the length of the cytoplasm within an axon before you've had too many of them kind of leak back out across the membrane, and then you have to regenerate some new action potential to keep getting ions to flow down the axon. And so we looked at the equation here for the length constant and basically identified that there are these two resistances that determine what the value of the length constant will be, and therefore how fast we can propagate action potentials. The first of these was the resistance of the neuron membrane, and that's in the numerator here. So the more resistant the neuronal membrane is to the movement of ions across it, the greater the length constant will be and the faster the action potential propagation speed will be. And so in that regard, we're basically saying, hey, if these sodiums come in through this open voltage-gated sodium channel, if the membrane is really resistant to those sodiums kind of passing back through it, then that's going to force them to keep traveling within the axonal cytoplasm. That's going to help those ions get down towards the terminal, kind of carry that action potential faster. And then the other thing we said was that the internal neuronal resistance is also important. So that is to say, how easily can ions move within the cytoplasm? The less resistance there is to ion flow within the cytoplasm, again, the more likely the ions are to travel within that cytoplasm as opposed to leaking out. So effectively, looking at the length constant equation, we want there to be a high membrane resistance and a low internal neuronal resistance. That's how we'll maximize our length constant, and by extension, that's how we'll maximize our action potential propagation speed. So that kind of recaps what we talked about right at the very end of the lecture on Friday. So now I want to get into some more specifics here in terms of like how does the human body, or more broadly, how do animals kind of manipulate that length constant equation, if you will, to achieve fast action potential propagation. So we're going to start by talking about axon diameter, which is a major way to regulate action potential propagation speed. What you're looking at here is clearly not a human. This is a squid, and it's been partly dissected here so that you can see these important structures in the center. So let me just bring up this drawing so we get a sense of what we're looking at here. So this structure right here, this is the stellate ganglion. So it's this structure here. And you can see that what emerges from the stellate ganglion is the stellate nerve. So that's what you're seeing here, the stellate nerve. And you can see here that they're showing us what the stellate nerve looks like if you cut it in cross-section. You'll notice that there are a whole bunch of these small diameter axons on the periphery of that nerve, but then you have this one large diameter axon in the center, right? So this is often referred to as the giant axon of the squid, right? So giant axons, large diameter axons, they propagate action potentials very rapidly. So the larger the diameter of an axon is, the faster it can propagate action potentials. And so that large or giant axon here in this squid that's part of the stellate nerve innervates the muscles of the squid that are involved in jet propulsion, which is the mechanism it uses where it kind of squeezes water out the back end to kind of propel itself forward. And this is a crucial part of the escape response of the squid, right? So if a squid detects a predator or some other cause for concern and needs to be able to kind of get out from where it is really quickly, it activates this jet propulsion mechanism, having those muscles innervated by this giant axon with this large diameter that can transmit action potentials very rapidly, ensures that there's very little delay from the time that you detect the threat to the time that you are jetting away from that threat. Now, why is it that a large diameter axon can propagate action potentials faster than a small diameter axon? Well, the answer is going to lie in this length constant equation somewhere. Clearly, there's got to be differences between either membrane resistance or internal neuronal resistance between small diameter and large diameter axons. So let's explore this. So here I've just drawn out on the left a small diameter axon, and on the right we've got a large diameter axon. And we're going to think about how these two resistances, the RM, the membrane resistance, and the RI, the internal neuronal resistance, how do these two resistances change as we go from a small to a large diameter axon? Well, let's think about RM first, the resistance of the neuronal membrane. And what you can probably appreciate is that the larger the amount of membrane you have, so the more membrane surface area you have, the more easily it should be for ions to cross that membrane, right? Because there's just more total area over which they could leak back out of the cytoplasm. And so we're saying here that the RM value, the membrane resistance, is proportional to the surface area of the axon, and surface area is proportional to length squared, right? So as diameter is increasing, which is a measure of length, ultimately surface area increases as a function of the diameter of an axon squared, okay? And so as we increase diameter, we are going to be decreasing the membrane resistance because there's more surface area available through which ions could leak out of the cytoplasm. Let's think about the other resistance here, Ri, the internal neuronal resistance. This, again, is a measure of how easily can ions flow within the cytoplasm of the axon. And what you can hopefully imagine is that this is going to be based on the volume of that axon, right? The more space, the more volume, the more space there is inside that axon, the easier it should be for ions to move around and flow through that cytoplasm, right? And so we're basically saying that the internal neuronal resistance, Ri, is a function of the volume of an axon, and volume is length cubed. So what we're saying here is, you know, the RM value, the membrane resistance, is proportional to surface area, right, which is length squared. The internal neuronal resistance is proportional to the volume of the axon, which is length cubed. And we're basically saying that both these resistances should go down in terms of their value as the diameter increases. You know, the RM goes down because you've got more total membrane area over which the ions could leak. And the Ri goes down as diameter goes up because you've got more space inside the axon for the ions to flow through the cytoplasm. So both RM and Ri are going to decrease in terms of their value as axon diameter gets greater. However, because Ri is proportional to volume and therefore length cubed, whereas Rm is proportional to surface area and therefore length squared, the Ri decreases to a faster degree, right? Volume changes more than surface area does as objects get bigger in size. So your Rm is only dropping a bit, but your Ri drops a lot. And so if we go back to our equation, well, if Rm only drops a little bit, but Ri drops a lot, because Rm's in the numerator and Ri is in the denominator of this equation, the overall length constant is going to be greater. So larger diameter axons can propagate action potentials faster, mostly because as you get bigger in size, the resistance to the movement of ions within the cytoplasm drops more dramatically than does the decreased resistance of the ion flow across the membrane. And that leads to an overall increase in the length constant, and therefore an increase in action potential propagation speed. Does that make sense? I saw one head nod, so I'm going to say that's fine. Okay, here, just to look at this again in a bit more of a practical context. So here you're looking at an electron micrograph image, and they've taken a cross-section through the pyramidal tract of a macaque, which is a type of monkey, so, getting close to us. The pyramidal tract basically is this network of axons that kind of connects the motor output regions of our brain to the various muscles of our skeleton, right? So it's involved in movement. And you can definitely see, and we'll talk more about this later, that there are a lot of very large diameter axons present within this pyramidal tract, which again doesn't surprise us because ultimately we know from our own kind of lived experiences that, we're very quick in terms of motor response, right? If I was to see someone throwing something at my head, I can very quickly put my hand up to block it, right? We are able to trigger our skeletal muscles very rapidly. And so that kind of jives with the fact that we've got a lot of these large diameter, fast propagating axons that are connecting our motor output regions in the brain to our skeletal muscles. However, you will also notice that there are several small diameter axons that are mixed here in this pyramidal tract. So it's not all large diameter axons. And a broader question you might ask yourself is, well, isn't faster always better? Like, why would we ever not want fast action potential propagation? And I think the answer is, yeah, faster is always better, right? This is why I upgraded my internet yesterday, right? Faster is always better, right? Despite my wife's case, her argument was, why does anyone need internet that fast? Well, there's lots of reasons why we need internet that fast. But faster is always better, right? I feel like I'm now a Bell commercial here for a second. But faster is always better. But of course, in the case of faster internet, what's the cost? More money has to be spent on that. What's the cost in terms of having large diameter axons all over the place? Well, they occupy a lot of space, right? A large diameter axon occupies a lot of space. So there is this trade-off in terms of, okay, yeah, a large diameter axon allows for faster action potential propagation speed, but at the same time, it takes up more space. So then if you want to have all these axons be large diameter, so they're all fast, either you're going to have, okay, a bigger nervous system. Okay, well then how do we accommodate that bigger nervous system? Well, maybe I have to be a bigger animal overall now. Okay, there are costs associated with that. Or if I want to stay the same size, maybe I have to have a larger nervous system, but I have to shrink the size of some other part of my body to maintain the overall same body size. What I'm hoping you can see there's going to be trade-offs, right? So basically, in the course of animal evolution, in the case of human evolution, decisions have to be made at that evolutionary level. Okay, well, which muscles do we really need to be able to contract the fastest? And, which systems do we need to be able to, which sensory systems do we need to respond to the quickest? Let's make those diameters associated with those systems and those axons larger, and let's not invest large diameter into maybe muscles that don't need to contract so rapidly, or sensory systems that we don't need to be so quickly responsive to, because we don't want to have this huge, large nervous system, or take away from the size of other organs, or whatever the case might be. The other way to speed up action potential propagation is through the myelination of axons. And so here we have a little drawing first. So in blue, we have an axon here. And then the myelin sheath is here in green. And what is the myelin sheath? You can kind of see when you look at it. It's basically another cell, this green cell, has wrapped itself around the axon of this neuron many, many, many times, right? That's what you're seeing here. That's the nature of the myelin sheath. It's a cell that has wrapped itself many, 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 many times around the axon of a neuron. And so when you look at this electron micrograph image of this myelinated neuron here, I mean, you can see, right, these kind of black and white lines running around here. I mean, these are the multiple layers of plasma membrane of this other cell here that are wrapped around many times the neuronal axon, right? So that's the nature of myelination, right? So when we talk about the myelin sheath, being very fatty, I mean, that's partly because it's made up of predominantly phospholipids, right, from the membranes of this other cell. So it is very fatty, and we're going to talk more about the significance of that perhaps a little bit later. But I want to first kind of talk about, well, what is the nature of this other cell? This green cell that you're telling me wraps itself many times around the axon of this neuron, like, where is that cell coming from? What's its identity? We already talked a little bit about this, but as a reminder, it depends on where you are in the nervous system. So in the central nervous system, that other cell is the oligodendrocyte, right? And so that's what's wrapping itself many, many times around the axon here. What you'll notice with oligodendrocytes is they have these processes that stick off from their cell body, and then each myelinated section of a myelinated neuron is just one of these processes that has wrapped itself many times around the axon. And you can see here a couple of things. One is you can see that an individual oligodendrocyte could actually contribute to the myelination of several different axons. But also, along the length of a given axon, you could have many different oligodendrocytes contributing to its myelination. All right, so that's one thing you notice there. In the peripheral nervous system, we have a different cell type that's involved in the myelination, and that is the Schwann cell. And it's a little bit different here because what you'll notice is each myelinated section is just one Schwann cell that has wrapped itself around many times, and that's it. That Schwann cell contributes to that one myelinated section. It doesn't contribute to the myelination of any other axons, so a little bit different organization than what we see in the central nervous system. The other thing I'll draw your attention to right now, and we'll come back and talk about its significance in a moment, is that you'll notice that the myelin sheath is not a continuous sheath. You'll notice these little gaps where you can actually see the axon there in red, and you can see that down here too, little gaps in the myelin sheath. These are known as the nodes of Ranvier, right? And we're going to come back in a moment and talk about their significance. But before we do that, I want to just talk about, well, how does myelination speed up action potential propagation, right? How does it actually allow for action potentials to travel faster down the axon? Well, again, in trying to answer this question, we're going to come back to our length constant equation. So we know, again, there are only two components to this equation. One is the internal neuronal resistance. I can't see where myelination would play a role there. It's not changing how much space there is within the axon, so probably not playing much of a role here. But the other component, that resistance of the neuronal membrane, okay, now I can see where the myelin sheath comes into play. Because if I'm wrapping the membrane of another cell many, many, many times around my axon, I'm effectively making it way, way harder now for ions to move from the cytoplasm of that axon into the surrounding extracellular space, right? Because we already established last week, like, it's hard for ions to go through the membrane on their own anyways, unless they're elite channels. If I'm then wrapping layer upon layer upon layer upon layer of membrane around the axon and creating this very hydrophobic sheath, right, then it's going to be very challenging for charged ions to migrate across that sheath to get into the extracellular space. So myelination works effectively by drastically increasing the membrane resistance. And what's interesting about this model for how myelination works is it's been around for a very long time, right? It's often referred to as the single cable model, and it's been around since the 1930s to the 1950s, right? Which is kind of like the early days, if you will, of electrophysiology. And so the little drawing I have here just kind of shows what I was already talking about, right? Here's your internal neuronal resistance, RI, right? And again, myelin doesn't do anything to that. You've got your resistance here across the plasma membrane of the axon, right? Which again is not really being impacted at all by myelin. And then lastly, you've got the actual resistance of the myelin sheath itself, this RMI, and that's where myelination comes in. You've added basically another resistance, right? You had the initial resistance of the plasma membrane itself, making it hard for ions to get across the plasma membrane, but now you've got this additional resistance through the myelin sheath, making it even harder for ions to leak from the cytoplasm into the extracellular fluid. And so again, that's going to encourage those ions to continue flowing down within the axonal cytoplasm. Now, as I said, this model, this single cable model of myelination originated a long time ago, right? We're talking almost a century ago now. In 2004, a paper by McIntyre et al., they kind of added a bit more nuance to that original model. They kind of reminded people that the myelin sheath in blue here, and then there's your plasma membrane of your axon, they kind of reminded people, hey, people, there's a space in between there. It's called the periaxonal space. So the myelin sheath is not like abutted right up against the plasma membrane. There's actually a space between them, that periaxonal space. And this had been kind of largely ignored in models of the myelin sheath until this McIntyre paper was published. And what they said in this paper is, thinking about that periaxonal space, there's now this additional resistance that we need to think about that's important, which is the resistance to flow of ions within that space. So what they were kind of arguing in this paper is that, ions can, say, leave the axon and flow across the plasma membrane and enter into this periaxonal space. From there, they could either try to make their way through the myelin sheath, which again has its resistance, or these ions could flow within this periaxonal space and try to then sneak their way through what's called the perinodal space, where the myelin sheath kind of hits the axon, where it kind of like links on there, leak out through there, and then it's back out into the extracellular space. So they kind of envision that there are two kinds of ways that these ions can leak back from the cytoplasm to the extracellular environment, right? And so this is called the double cable model, reflecting that there are these two different paths that these ions can take. Now, the significance of the periaxonal space is that if you have very high resistance in this space, if it's very hard for ions to flow in this space, you could imagine ions leaking out of the axon into that periaxonal space, and then if they get stuck there and can't really move well to try and leak out to the external environment, then ultimately you get a buildup of ions in that periaxonal space, and then that discourages other ions in the cytoplasm from leaking into that space, right? They're like, hey, this is a crowded space. There's already lots of charged ions out here. Screw that. I'll just keep going down along the cytoplasmic axon here. So the periaxonal space and its resistance to ion movement within it is perhaps an additional factor in terms of how the myelin sheath might be, again, favoring action potential propagation. And I want to just go on a little bit further here to say that there have been some recent studies where they've actually demonstrated that simply changing the resistance to ion flow within that periaxonal space without making any changes to axon diameter, without making any changes to the thickness of the myelin sheath and therefore its resistance, by just changing the resistance of ion flow within that periaxonal space, you can actually change action potential propagation speed, right? So the single cable model couldn't explain that. Like the single cable model would say, hey, if you don't change myelination or if you don't change diameter, then speed shouldn't change. But we actually do see lots of examples where the diameter stays the same, the myelin sheath stays the same, and yet we do see action potential speed changing. So that tells us right away that our model is insufficient. We've got to add to it, which McIntyre did. But let me just kind of show you this. So this is a graphical abstract from the paper I was talking about. And so they were focusing really on the relationship between action potential, conduction velocity, which they're showing here with these gray arrows, and the size and therefore the resistance of the periaxonal space. So it starts here with just the baseline activity. But then what they saw in this study is that when they subjected these mice to transcranial magnetic stimulation, it slowed down action potential propagation speed. Again, it didn't change the diameter of the axons. It didn't change the thickness of their myelin sheaths in any way. The only thing that they observed changing was that the periaxonal space became larger in volume. So the myelination kind of pulls further away from the axon, creates this larger volume to the periaxonal space, and with that larger volume in that space, the ability of ions to move around within that space goes up. So the periaxonal resistance goes down. So now you have, ions leaking out into that space. They can quickly flow within it to then sneak out through the perinodal space, and then that allows for more ions to keep following that route, and then that's what causes the conduction velocity to go down. Because ions are now finding their way easily into the periaxonal space, and then kind of rapidly flowing within that space to the perinodal space and back into the extracellular fluid. They also showed in that same study that when they subjected the mice to spatial learning, so teaching them how to navigate through a maze, they found the opposite. They found that conduction velocity in brain regions went up, right? So they were better at navigating the maze more quickly. They get to little junction points and make decisions about which way to go faster. And again, they saw no change in axon diameter, no change in myelin thickness in those studies, but they saw the periaxonal space volume decrease, meaning that there's this very small volume there, so the ions that leak into it are kind of stuck there. They can't easily move out. And so you've got this high resistance in that space that makes it harder for other ions to leak into that space. And so the ions then say, you know what, I'll just stay in the axonal cytoplasm. I'll keep flowing down the length of the axon. And they saw faster conduction velocities. All right? So, yeah, I guess the point here, in a broad sense, is, our understanding of myelination and how it speeds up action potential propagation, is ever evolving, right? It was stagnant for maybe a century or a good 70 or 80 years, and then it just takes people to kind of come in and rethink things a bit, revitalize things, add some nuance and additional components, and we've probably now got an overall better sense of how myelination is doing what it does. So I want to go back for a moment to this idea that the myelin sheath is not a continuous sheath, right? This idea that we mentioned earlier, that there are these nodes of Ranvier that are present, these little gaps in the myelin sheath. And as they very clearly illustrate in this figure, this is the only location along the length of a myelinated axon where we see any voltage-gated sodium channels. Okay, they're not present within the myelinated regions, so there are no action potentials happening within those myelinated sections. All the voltage-gated sodium channels within a myelinated axon are located in the nodes of Ranvier. Now the question to ask ourselves here is, why do we need nodes of Ranvier? Why can't we just have a continuous myelin sheath, running from the axon initial segment all the way down to the axon terminals? The answer to that question is because although the myelin sheath does, as we've discussed, make the neuronal membrane resistance much greater, it doesn't perfectly eliminate the ion flow across the membrane. You're still going to have some ions flowing across. There's greater resistance, right? So it would almost be, if you imagine that I stood by the doors during the whole lecture and lectured from there, then probably you'd see many fewer people sneak out earlier because they'd be like, oh, well, he's right there. I'm not going to go past him when he's right there. But if I stand, over here with my eyes closed and my back to the door, then people are going out all the time, kind of a thing, right? That's the idea. But even if I'm staying at that door, there's still going to be people who go out, right? So the resistance to leaving might be greater, but it's not going to stop people from entirely going out or even maybe coming in. So because the membrane or the myelin sheath is not perfectly resistant to the flow of ions across it, we have, say, sodium ions coming in at this node of Ranvier, right, through these open voltage-gated sodium channels that are there. And yes, they're going to be encouraged to keep flowing down the axonal cytoplasm because it's not easy to get out across this thick layer of myelin. but some of them are going to slowly go. And so the depolarization that occurs at one node of RANVA as part of the action potential there, that depolarization does spread down the axonal cytoplasm, but there is this decremental conduction that's happening. You do have some sodiums leaking out back into the extracellular fluid, and so the depolarization is gradually decaying. And the idea is that if you had just one action potential take place at the axon initial segment, and those sodiums all came in there, and you were thinking, okay, I hope those sodiums can get all the way down the length of my axon to the axon terminal to trigger the release of a neurotransmitter, that's not likely going to happen. They're going to find their way out, enough of them, to actually cause enough decay of the depolarization of that action potential that by the time you actually got to the terminal, the membrane potential would just be back to rest. There'd be nothing to signal the release of a neurotransmitter. So we need to keep regenerating action potentials along the length of the axon to offset that decay. And that's why we have these nodes of RANVA. And we position them strategically, right? We make sure that by the time, before, so these sodiums come in and depolarize the membrane, before that depolarization decays below threshold, there needs to be another node of RANVA, where we have another set of voltage-gated sodium channels that we can trigger open to regenerate a new influx of sodium. It's kind of like if you imagine if you've ever been on like a road trip in northern Ontario, right? Never pass by a gas station because you never know when the hell you're going to see another one, right? You're hoping the gas stations are strategically, planted so that you're like, okay, my gas tank holds 500, or whatever, 500, that's a big gas tank, holds 50 liters, right? I'm driving along hoping that before I run out of gas, there's another gas station for me to refuel, right? That's kind of what we're saying here. You've got to be able to regenerate new action potentials, new influxes of sodium, new depolarizations before the previous depolarization has decayed below the threshold where it can't actually then, initiate a new action potential. So the lack of perfect resistance of the myelin sheath is what dictates the need for these voltage-gated sodium channel clusters within the nodes of RANVA. Now, the other thing we have to appreciate about these nodes of RANVA and about the myelin sheaths, kind of just as I was saying, they have to be kind of strategically positioned, right, so that you have a node that's located at a position before the depolarization decays below threshold, you couldn't generate another action potential. So with that idea in mind that we have to strategically locate the position of these nodes and therefore the location of these myelin sheaths, it's kind of like when we were talking about the axon initial segment earlier and how there's this anchoring system to kind of hold the axon initial segment in place so that the axonal and dendritic zone proteins can't just kind of mix together. Something very similar is happening here. So you can see here in this picture at the bottom, here's my axon cytoplasm down here in blue. Here's the myelin sheath here in yellow. And then here's this region called the paranode, right, where the myelin sheath ends and the node of RANVA begins. And what you'll notice is that there are these proteins that basically anchor the ends of the myelin sheath in place to the underlying membrane of the axon. So that the myelin sheaths are anchored in place, right? And therefore the nodes are kind of also fixed in place, and these things can't just kind of move around, and then suddenly you're like, oh shit, it'd be like if the gas stations could move around, like, oh, that gas station was there within the distance I could drive, but then it floated off and down the road. We have to anchor these myelin sheaths in place. And so the picture here shows us the proteins that are involved in that. So the myelin cells, the Schwann cells, the oligodendrocytes, they make this protein called NF155. And then in the membrane of the axon down here are these two proteins, Casper and contactin. And you can see how the NF155 and the contactin link together. And therefore, or thereby, the myelin sheath in this paranodal region is physically attached to the underlying axonal membrane. And this, again, anchors the myelin sheath in place, right, allowing us to have, again, fixed positions for our nodes of RANVA. I'll show you this because I think it's kind of a cool little image here. So this is from a study where they were using immunofluorescence. So they would use antibodies, one that could recognize this Casper protein, one that could recognize voltage-gated sodium channels, and then they attached either a red or a green fluorescent marker to them. And this allowed them then to visualize the relative position of these two proteins. And look how beautiful this image is. You can see the node very clearly here, the node of Ranvier, because the voltage-gated sodium channels are there, and they were tagged with this green fluorescent antibody. And then you can see that on either side of the node, you have the Casper proteins that are part of this anchoring system. You can see them very clearly on either side of the node because they were tagged with this red fluorescent protein. And then you can see that if you imagine the rest of this axon running through here, both right and left, neither of those proteins are present out there. Again, the voltage-gated sodium channels are exclusively in the nodes. This Casper is part of this anchoring system that's only at the paranodes, so the whole myelinated section isn't visible in this diagram. You could maybe, again, this is one of those things where it's like, where can I think about this content? You might say to yourself, oh, can I imagine what kind of antibody I could use to maybe, add to this study to be able to visualize, the myelinated regions too? Right? That'd be a good example of a kind of just you thinking about the course content and anticipating, the kinds of questions you might see on a quiz or something. But yeah, pretty cool little image there that I wanted to show you. And so where I want to go next here is into a little bit of terminology that's relevant to all the things we've been talking about here. So if we start at the top of this figure, you can see that they're out here in the dendritic zone. They're looking at a dendrite. And so we know that in the dendrites, we have graded potentials, not action potentials. And so they're showing us a graded potential here. So a stimulus was applied at this point. And so you can see there was this kind of depolarization that took place. And then as we know, graded potentials will decay as they travel. And that's what they're showing us here. So we have this maximum depolarization at the stimulus, but it gradually decays back down to rest as it goes. And we already know the terminology for that. It's called decremental conduction. And we've already been through all the physiology related to that, so this is nothing new. Here we have an axon now, but it's an unmyelinated axon, right? No myelin sheath. And so same thing, we've got voltage-gated sodium channels now. These are the purple things. These voltage-gated sodium channels are present here. They weren't present, of course, in our dendrites. They are, generally speaking, only present in the axon and axon initial segment. So here, we've tripped open the first of these voltage-gated sodium channels, and a depolarization has occurred. That's the first phase of our action potential, as we know. So you've got these sodiums that have come in, but what they're trying to show us here is that that depolarization caused by the opening of this voltage-gated sodium channel is going to spread. Those sodiums are going to come in and start traveling down the axon cytoplasm, as we know. But then, because there's no myelin sheath here, especially, a lot of those sodiums will start leaking back out across the membrane pretty rapidly. So they're also showing us that there's decremental conduction taking place there. But then, as we just talked about moments ago, the key is that if you have another voltage-gated sodium channel present at a distance that's before the decay takes you down below threshold, you can then use that previous depolarization to trigger open this new voltage-gated sodium channel. You get a new action potential, a new influx of sodiums. So you've regenerated your depolarization. Then again, it travels and decays, but as long as there's another voltage-gated channel before it decays below threshold, we can trigger that one open and get another action potential to occur, a new influx of sodium, and we can keep doing that over and over and over. This is known as continuous conduction because essentially you have action potentials being generated along the entire length of your axon, right? Because you've got this rapid decay of the depolarization because there is no myelin sheath. So you have to have voltage-gated channel after voltage-gated channel after voltage-gated channel after voltage-gated channel present in your membrane, and you keep generating action potentials all along the length. That's continuous conduction. The very final figure here shows a myelinated axon. So we can see the myelin sheaths. We can see the nodes of Ranvier here, which is where the voltage-gated channels are located. And here we have now what's called saltatory conduction. Now, it says here that saltatory conduction refers to the action potentials only being generated at the nodes of Ranvier. So, for example, here we have an action potential that will occur here. Nothing will occur, no action potentials will occur through the myelinated section. The next one will occur way down here. And then nothing through this section, and then way down here. So we don't have continuous conduction anymore. We have action potentials only occurring sporadically along the length of the axon at the nodes of Ranvier. The reason this is referred to as saltatory conduction is actually a bit of a misnomer that reflects kind of historical misunderstandings of things. The term saltatory means to jump. So the early electrophysiologists, when they saw action potentials only happening, periodically along the length, they mistakenly thought that the action potentials were jumping over the myelinated sections. And so they called it saltatory conduction. But that's not what's happening. So that's a historical misunderstanding, and yet the term continues to persist. We see this a lot in science. What is actually happening is that we have, just like we did here in the unmyelinated axon, we have this voltage-gated sodium channel being tripped open, and sodiums are coming in, so we have a depolarization. And we have the sodiums, again, traveling down the cytoplasm, spreading that depolarization. But the key now is that because you have that myelin sheath there, right, which limits the ability of these ions to leak back out, those ions travel further down the axon before you decay and before you get to a point where you're like, okay, I need another set of voltage-gated sodium channels here because if I go any further, I'll decay below threshold. But the idea is that each individual influx of sodium can travel much further down the length of the axon because it's not decaying as rapidly because of the resistance caused by the myelin sheath. So now you don't have to have voltage-gated sodium channels all along the length. You can space them out further because the length constant is essentially greater, right? The ions can travel further down the cytoplasm. It's almost, if you imagine, going back to my gas tank analogy, it'd be like if I went out and found your car in a parking lot and jammed a hole in the gas tank, because I don't know, for some reason I hate you, I don't know why. None of you. Maybe it'd be like the second years or something. But I'll just jam a thing into their gas tank and it's leaking. You'd be driving home and you'd be like, oh, well, I'm leaking gas so much faster than usual, right? So then ultimately I'm going to have to pull into the gas station and refill. And I get back on the road and I'm driving like, oh, the gas is leaking. I got to pull off. It's going to take you forever to get home. But if you were to patch that hole up so there's no leak now, the gas flow out of the tank is there's more resistance to its flow out, then obviously you can kind of drive further before you have to fill up, and then you're going to get home faster. It's kind of the same basic idea here, right? That if we can put a patch here to prevent the sodiums from leaking out, and therefore they can travel further before we have to regenerate a new action potential, again, we're spending our time moving down the axon rather than leaking across and then having to regenerate new action potentials. It's going to lead to faster action potential propagation. So we do have to appreciate that decremental conduction does occur, right, between the nodes of Ranvier, just like it occurs here between the voltage-gated sodium channels in the unmyelinated axon. Really the difference between these two is that the decay is much slower because of the resistance provided by the myelin sheath. I'm going to stop there because I can't tackle this in 2 minutes. So we'll stop there. We will try to finish this up tomorrow. I don't know how long that'll take, but I'm going to post the notes for the next lecture topic tomorrow morning. So you'll have them before Thursday, just in case we get that far. Yeah, we only have 3 slides left, so it shouldn't take us too long. Expect that Thursday we'll start into our new topic at least a little bit towards the end. Enjoy the rest of your afternoon.